Welcome to the de Havilland Aircraft Museum. Most aircraft enthusiasts will immediately recognize this model, and particularly the wing planform. It is, of course, a model of the DH98 Mosquito. But if you look at the wings, they're somewhat unusual. There's a very sharp trailing edge and a straight leading edge. In fact, some people who've built this model have even tried to put the wings on the other way around. You'd naturally expect that. We're used to leading edge tapering back. So why are these wings like this? As far as I know, this is the only aircraft with wings this extreme, with the possible exception of the Handley Page Hampton, which flew a couple of years earlier. So why build a plane with triangular wings? That's the subject of the research we've done for this video.
During the early days of aviation, wings were basically rectangular. The chord remained the same throughout the span. Even afterwards, it proved to be a basic, easy to design and simple to manufacture approach, like this de Havilland Chipmunk from the post-Second World War. But during the 1920s and 1930s, the science of aviation had progressed. Theoretical research suggested a tapered wing was more aerodynamically efficient. A tapered wing meant that the majority of the lift was concentrated near the centre of the aircraft. This reduced the stresses on the outer wings, meaning they could be built slightly thinner, and it reduced overall drag. By the 1930s, beautiful tapered wing designs were common. Research then suggested that an elliptical wing was the most efficient. This was demonstrated in a number of aircraft, such as the Heinkel HE-70 mailplane. The classic example, of course, is the famous Supermarine Spitfire. There were drawbacks in a tapered or elliptical wing. They were difficult to manufacture. The elliptical wing Spitfire was significantly more expensive than its contemporary, the Hurricane, which had a conventional tapered wing. Tapered wings, because they generated less lift near the tips than the root, could lead to what was known as tip stall at low speeds. This meant the tips would stall before the rest of the aircraft. The result would be the aircraft just span into the ground at low speed, which could be fatal. On the DH87 Hornet Moth, this was so significant a problem that de Havilland introduced the DH87B, the same aircraft with older rectangular style wings. This was slower due to the increased drag, but safer for a novice to fly. Nevertheless, tapered or elliptical wings were definitely the correct aerodynamic approach. You can see this in the high-speed racer, how the wings taper towards the tips.
So if I had been a designer for de Havilland at the time and I was charged with designing the wing, I would probably do something like this. So this is the starboard fuselage, and I would probably think of the DH98 Comet Racer and come up with a wing that's sort of tapered like that. Maybe I put a bit more taper in it here, maybe make it a bit like that. So you'd have this gradual shape, gradual tapering shape. And this is exactly what you see today on the DH88 Comet Racer. On the other hand, you look at what de Havilland actually drew. Again, let's say this is the starboard fuselage, but they had a very, very strong leading edge and a very sharp taper back. So the wing is almost triangular in format. So why did they do that? They've got a straight leading edge and they've got a very sharply tapered trailing edge. It's a tapered wing. It's like no other wing that you'd ever seen, with the exception of perhaps the Handley Page Hampton, which I mentioned earlier. So why did they do that? So to begin to understand the design of the wings, we need to look at a couple of basic concepts: lift and drag. The purpose of the wing is to give lift to the aircraft, and the average location of that lift, let's say it would be about here, would be the center of lift. At the same time, you've got all the various things that contribute to the weight of the aircraft. and the weight of the aircraft would be centered, shall we say, somewhere here. So you have the center of lift given by the wings, counteracted by the center of gravity of the aircraft. And those two need to broadly line up. If, for example, the center of gravity was ahead of the center of lift, the plane would fly nose down. If the center of gravity was behind the center of lift, the plane would begin to nose up and probably stall and crash. In practice, most designers put the center of gravity slightly forward of the center of lift, and then they counteract that by using the rear stabilizer. So let's have a look at wing design. If we take a basic wing like this and wing here, starboard wing, the center of lift of that wing is approximately a third of the way back from the leading edge. So here the center of lift is about here, 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 and here. So if you average that out, the center of lift of this wing is approximately like that. So let's now have a look at an alternative. So the second thing we can look at is a tapered wing. If we look at a tapered wing, something like this, again, the basic rules are the same. The center of lift is about a third of the way back, so it's about a third of the way back there, about a third of the way back there, about a third of the way back there, and there. So the center of lift seems to taper back. The average center of lift is probably about there, a little bit further back than what we had with our earlier rectangular wing. Now let's look at another example of a wing which most people are very familiar with, and that is a very swept back wing, maybe even sort of a delta format wing. For that type of wing, the center of lift will be again about a third back, about a third back, about a third back. And so you'll see that the average center of lift of that wing is somewhat further back than you had with, say, the tapered wing, somewhat further back than you would have had with the rectangular planform wing. So given all of that information, let's have a look at our final drawing, which is what the actual Mosquito wing looks like. So I'm exaggerating slightly, but we've got a very straight leading edge and we've got a tapered trailing edge. So the center of lift of this wing will be about a third back, about a third back, about a third back, about a third back, something like that. The center of lift will probably be about there, maybe a bit lower, maybe a bit more like that. Okay, so with this particular wing, this is the design we drew earlier. With this particular wing, we've got a forward sweep. The center of lift is further forward than it would have been in a rectangular wing. It's further forward, certainly, than it would have been in the tapered wing that we talked about earlier. They built a wing which, to all intents and purposes, appears to be designed to have the greatest lift as far forward as possible. Why did they do that? Was it manufacturing simplicity, or was there an aerodynamic reason? Let's go and have a look at the actual aeroplane, see if we can find out why. So here we are in front of the FB6 version of the Mosquito. This was the most common version, and I'm interested to find out where the weight is. First obvious thing, of course, is the fuel tanks, but these are actually under the wing spars, so that's central. The bomb bay itself, the aft portion of the bomb bay is here. Again, it aligns with the wings. The Hispano cannon, they're really quite heavy, but the actual cannon themselves are in the forward bomb bay rather than in the nose, and they shoot through these channels here actually into the nose. So the weight is concentrated backwards. As I move forward, obviously we've got the radiators. The pilot and navigator are lined up pretty much near the leading edge of the wing. And beyond that, we've got the machine guns with obviously their cased ammunition. That's going to be a significant weight forward of the leading edge as well. But actually there's something more significant. As I look around here, we've got the two Rolls-Royce Merlin engines, each of which weighs about 3/4 of a ton. And that additional weight lined up with the wing spar, that's going to be a significant percentage of the weight of the entire aircraft. And that could well be why they designed the wings that way. Despite all our research, we've not been able to definitively prove why the Mosquito had its triangular wings. But we've looked up many sources, we've spoken to many people, no actual explanation has come forth, but we do have a theory, and it works like this. The Mosquito wings were designed with this sharp trailing edge in order to bring the center of lift as far forward as possible. And part of the reason for that was because it then mimics the shape that we're all familiar with in aircraft wings, which is the famous Spitfire elliptical wing. It's not that far off it. It is easier to manufacture if it's got straight edges, but also significantly we have the massive weight of those Merlin engines, which are bringing the center of weight, center of gravity, forward. And so we designed a wing with the center of lift as far forward as possible to counteract the weight of those massive Merlin engines. Of course, there could have been another way we could have addressed this problem. Instead of putting the Merlin engines that far forward, what we could have done was buried them underneath the wing. That could have solved the problem, but that would have resulted in a greater frontal area, a bit like the DH98 Comet Racer. That would have increased drag. By moving the engines forward, putting them in line with the leading edge of the wing, we have the weight problem, but we've reduced the frontal area and we've reduced drag, and we've got a faster machine. So for the time being, the mystery of why the Mosquito wings are the shape they are remains a bit of a mystery. If you've got access to any original source material about the Mosquito design that you'd like to share with us, please do. If you've got any further thoughts, please leave comments below in the comments section. Alternatively, come back to the museum, have a look at the Mosquito yourself alongside all the other de Havilland aircraft. So we'll see you at the museum.
Stop press. Whilst we were doing research on this particular topic, we came across a number of interesting diagrams, including this one. This at first sight appears to be a Mosquito until you look at the wings. It was in fact a design study for an aircraft that was designated at one time the DH99. After the Mosquito entered production, de Havilland were very interested in developing the design with a new model. The DH99 was intended to be powered possibly by the Napier Sabre engines. You'll notice, however, that the wing design is completely different. Instead of the triangular wings, they've reverted to a very basic tapered design, not unlike some of the other wings that we've seen in de Havilland aircraft earlier. So, could the Mosquito have been designed like this in the first place? Who knows?
And visual.
I think he wants us to go. Sorry, we'll go. Oh, sorry. We're just going to close the door.
Just wait a minute.
And
Could you give us 2 minutes?
just give us 2 minutes. It's
2
just
minute shots.
literally.
2 minute shot.
We'll be quiet.
Thank you. Right. Okay.